production. This actually makes sense. Our bodies are smart. They don't make fat and burn fat at the same time. Therefore, by both processes, we can get an increase in liver fat. And again, with increased liver fat, we have the increase in VLDL production and secretion, and an increase in triglyceride and cholesterol. The increase in triglyceride levels throughout the day happen with the first day of fructose consumption. It takes probably longer for levels of cholesterol and LDL to start going up. But John Mark Schwartz has seen it in 9 days. With our increased liver fat, we also get an increase in the liver insulin resistance. And again, as I said, that is a problem not only because it causes increases in the VLDL production and secretion, but it also causes an increase in de novo lipogenesis. This is called selective insulin resistance. It shouldn't be happening this way because de novo lipogenesis is an insulin-sensitive procedure. It should be inhibited when insulin resistance occurs. But unfortunately, it doesn't work that way. And with insulin resistance, we get even more de novo lipogenesis. And what this does, it has the potential to set up a very definite vicious cycle where we have DNL causing the liver fat, causing the VLDL, causing insulin resistance. Anyway, this nice little circle that fructose can do a great job helping keeping that circle going and going and going, like our Energizer bunny. Also, with our increase in triglyceride levels, we have the increase in intramyocellular lipid and whole body insulin resistance. At the same time, by a completely different pathway, fructose overload leads to the increase in uric acid by the purine degradation pathway, to be specific. We've known for years that uric acid causes gout. There are a lot of researchers out there that think the uric acid levels might be a mediator, contributor to also type 2 diabetes, kidney disease, hypertension, and metabolic syndrome. So, all this is very mechanistically interesting, but it really doesn't necessarily tell us a huge amount about our diet because we actually don't consume pure fructose and pure glucose in our beverages or in our food. We consume high fructose corn syrup or sucrose. Therefore, our next study, we wanted to look at the effects of fructose and glucose compared to the sugars we actually consume. We also wanted to look at the effects in younger, healthier subjects. I can't begin to go through all the results from this study, though this is the same study in which we reported the dose response effects of 0, 10, 17.5, and 25% of energy requirement high fructose corn syrup consumption. Those dose response effects correspond or corroborate beautifully the epidemiology dose response effect that Dr. Hugh talked about this morning with regards to added sugar consumption and cardiovascular disease mortality. But today I'm going to focus on the first 6 groups with the asterisks. But before I do, I want to quickly show you the study design for this study. It was a much shorter study, only a 2-week intervention, but it did start out with a 3.5-day residence at our clinical research center. And again, our subjects were consuming the same standardized diet that I showed you before, and ends with another 3.5 days at the end of intervention at the research center. quickly, here are the changes in body weights in the 6 groups. These are deltas, so it's basically the 2-week body weight, minus the 0-week body weight. And as you can see, there was no significant effect of sugar. However, in that 25% high fructose corn syrup group, the change in body weight was significant compared to baseline. But the other thing I want you to notice is the fact that the subjects consuming fructose did not gain weight at all. And so when you look at the results I'm about to show you, know that these results were completely independent of body weight gain. And we're going to start with, again, the glucose effects. Just like in our older subjects, glucose consumption had dramatic and very strong effects on the 24-hour free fatty acid levels, on the post-meal glucose responses, and the post-meal insulin responses. Again, that's the glucose, the delta, and the blue bars. And as you can see, the effects were significantly higher than any of the other groups. These results, of course, are expected. We also, though, were able, with an extra grant from NIH, to measure de novo lipogenesis in subsets of the subjects from 4 of the groups. This was the 3 high-dose sugar groups plus the aspartame group. And these are unpublished data. They're novel in that during our 30-hour isotopic acetate infusion, the subjects actually consumed the same standardized meals that I showed you the pictures of, rather than steady state meals. Usually de novo lipogenesis is measured when you give subjects small identical meals equally every hour throughout your infusion period. So these are meal responses, and they tend to be higher than what we saw when we gave steady state feeding. And as you can see in red, again, black is when the subjects were consuming the complex carbohydrate diets. With red, that's the fructose. You can see dramatic increases in the de novo lipogenesis that continued to increase throughout the entire measurement period. In purple, in the bottom left-hand graph is the high fructose corn syrup results. You see a similar increase, but much less marked increase due to high fructose corn syrup. Absolutely no effect of aspartame. And the glucose results are interesting in that they did not change throughout the day. Unlike fructose and high fructose corn syrup, de novo lipogenesis did not increase throughout the day. Rather, it was higher than at baseline at the beginning of the day and stayed at a similar level. Therefore, the interpretation of these results with regard to glucose kind of depend on how you want to analyze it. If you analyze these profiles as incremental AUCs, what you see is on the left-hand graph, where there's no effect of glucose on de novo lipogenesis, very, very significant effects of fructose, strong effects of high fructose corn syrup, and of course no effect of aspartame. But if you measure it as a total AUC on the right-hand graph, you still see very strong effects of fructose, but the glucose and the high fructose corn syrup results are far more comparable. At this point, I don't want to answer the question of which one of these graphs is more relevant to human health. If any of you want to venture an answer, I'd be delighted to hear it. And now these are, again, the changes in uric acid, postprandial ApoC3, and the 24-hour triglyceride AUC. What you should notice in these three graphs is the red bars, which are the fructose. The dark is the high dose. The light red is the lower dose. And they're always the highest. So fructose is higher than the high dose high fructose corn syrup. Fructose at the lower dose is higher than the lower dose high fructose corn syrup. And the results for glucose are less significant or not significant. Those are, again, expected results. The more fructose overload in the liver, the higher these risk factors. However, these results for ApoB, LDL cholesterol, non-HDL cholesterol are not so expected. Look up there. The red bars are not the highest. The purple high fructose corn syrups are higher than the corresponding red bars for these three risk factors. And it was true in the fasting state and in the postprandial state. So I don't think it was a random happening. In order to try and figure out what's going on here, I tested for an interaction between the fructose and glucose, doing this not by entering our 6 groups as factors or class variables, but as covariates described by their relative amounts of fructose and glucose. That means that the 25% group was described as a 0 fructose and 1.0 glucose, and the 25% high fructose corn syrup is described as 0.55 fructose, 0.45 glucose, and then modeled it as our outcome is affected by the fructose, the glucose, and the interaction between fructose and glucose. And what we saw, sure enough, for these 6 outcomes, fasting and postprandial LDL, ApoB, non-HDL-C, sure enough, we see a significant interaction of fructose and glucose. Whereas we do not see a significant interaction for the triglyceride AUC, the ApoC3, or the uric acid. What this suggests is that Dr. Hugh was right when he said fructose might not be our only culprit when it comes to the effects of sugar. So we looked at glucose to try and determine which of the effects we keep seeing in glucose could be related to this interaction with fructose. And so we looked at the 24-hour free fatty acid, the glucose spikes, and the post-meal insulin spikes. All of these were significantly increased by glucose, but not by fructose, but no hint of an interaction. Well, I did basically simple regressions and multivariate regressions with the changes in our 6 outcomes, the LDL, the ApoB, the non-HDL cholesterol, with the free fatty acids, the glucose spikes, and the insulin spikes. And it's there in the middle, you see that it's the glucose spikes that was associated with our changes in the risk factors, not the free fatty acids and